Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on July 30th, 2025. So, just yesterday. Well, this paper introduces a new model series, Falcon-H1, where the 34 billion parameter version matches or outperforms models up to 70 billion parameters. The paper is titled Falcon-H1, a family of hybrid head language models, redefining efficiency and performance. And the results really challenge what we thought was possible for smaller models. The authors achieved this by using a novel hybrid architecture that combines the strengths of both transformers and state space models. Also, the authors shared their work on GitHub, and it's packed with useful resources. You'll find documentation, demos, and practical code snippets. They provide clear instructions for running the models with popular tools like transformers and llama.cpp, making it really easy to get started right away. On Hugging Face, the 34 billion, 1.5 billion, and 0.5 billion parameter models are all available for download, along with code examples to get you started. Alright, so digging into the specifics. This table lays out the architectural details for the entire Falcon-H1 family. It really highlights their careful design choices. For instance, notice there are two 1.5 billion parameter models. One is shallower with more processing width per layer, while the other is much deeper with 66 layers. You can also see the massive context length. That's the amount of text the model can handle at once, going up to 256,000 tokens. This is a direct result of that efficient hybrid architecture we talked about. Building on those details, this diagram shows us the core of that hybrid architecture. You can see that within each processing block, the two key components, attention and the state space model, or SSM, run in parallel. A state space model is a structure that's really efficient at handling long sequences of information. So the input is processed by both of these components at the same time. Then, their outputs are combined and pass through another processing block. This flexible parallel design is the key innovation here, allowing them to balance the workload. So these next plots show exactly how the authors figured out the best way to balance that workload. They experimented with different channel allocations, which is essentially deciding how much of the model's processing capacity to give to the attention component versus the state space model. On the left, we're looking at the training loss, which is a measure of the model's error, so a lower value is better. The main insight here is that dedicating too many channels to attention significantly harms performance. The loss goes way up. The chart on the right then compares three different ways to arrange the blocks: fully parallel, semi-parallel, and fully sequential. We can see the semi-parallel approach, that's the red line, consistently achieves the lowest loss, making it the most effective design. This careful optimization is what led them to the final Falcon-H1 architecture. Moving from architecture to another critical element, this table details the data mixtures used for training. For the larger 34 billion and 7 billion parameter models, you can see a dramatic shift. They start with mostly raw data, but by the end of training, that mix changes significantly. The share of raw web data drops, while rewritten and synthetic data, that's content improved or even generated by other AI for higher quality, increases to over 50%. This focus on knowledge-dense data, rather than just raw volume, is a core part of their successful strategy. Alright, so in addition to optimizing the data, they also found a way to make the training process itself much more efficient. This table shows the impact of a technique they call mixer parallelism. Now, mixer parallelism is a strategy for running the two main components of the model, the attention and the state space model, on different hardware at the same time. The table compares a baseline with no parallelism to two different versions. The result is pretty dramatic. The best version, called interleaved mixer parallelism, achieves a 1.43 times speedup, boosting training efficiency significantly. So, with all these optimizations in architecture, data, and training, how does the final model actually perform? Well, this table shows us exactly that. Here, we see the Falcon-H 134 billion parameter model compared against much larger competitors, some up to 70 billion parameters. And the results are really impressive. Falcon-H1 secures the top spot on challenging reasoning benchmarks, like for advanced math, science, and code generation. While bigger models sometimes lead on more general knowledge, this performance really highlights how Falcon-H1's efficient design excels at complex, specialized tasks. So, to wrap up, the Falcon-H1 models really showcase the power of smart hybrid design. By combining different architectural components and optimizing the training strategy, they've achieved top-tier reasoning performance with remarkable efficiency. That's it for this episode of the AI Research Roundup. I'm Alex, thanks for listening.